Okay, so the third part of our FE exam, civil engineering geotech portions, is about the settlements or consolidations of soil. And it is in the FE menu on page 261 and also the majority portions of 262. So it's up to this point. Okay, so and this part also divided into two major sections. You will be stopped by here. So before that, it is the talk about the compressibility of soil, or like the questions of how much settlements. And good reference for this portions of engineering concept is go back to my CE 366 lecture number 8. So that will be talk about in much more details on the theories of how the compressibility of clay or primary consolidations of clay take place. So this is the first portions of it, and the second portions of our this sections is the time rate of settlements, or the questions of how fast does settlements occur in the field, or given like a piece of soil elements, soil samples, how soon the soil consolidations to be complete. So the best reference is for my CE 3660 lecture number 9. So that will be spend a little bit more details to talk about the theories and how things work. So and all the YouTube all the lectures is available on my YouTube channels. Look for the class of the playlist of CE 3660 lecture 8 and lecture 9. Okay, so the FE menu here start with a picture, and this picture here pretty much capture the important concept of soil consolidations. So this plot here, you can see the y-axis is the void ratios, and the x-axis, very important, this is in log scale. So this is a semi-log scale graph. And the y-axis, this is the void ratio. You can think of this is related to the deformations. In fact, this is related to the deformations or the settlements given a soil profile, and it is related to the void ratios of the soil. And again, the x-axis is the stress or the pressure. So the stress or pressure that applied on your soil profile or soil site. If you work on a consolidation lab, then you apply on your soil specimens. And realize that's an important breaking point here, which is the piece of C, which corresponding to this point, and left to this point and right to this point, which means the stress level or the pressure less than or greater than this threshold give you two different slope, or give you this two different range, as you can see on the menu. One is called the V compressions, the other one is called as a compressions, and associate with two different slope, the C sub R or C sub C. So C sub R stand for the recompression index, and C sub C stand for the compression index. So which represent the slope right there, of the line right there. And thus indicate very important soil behavior is when you apply a stress that is greater than the soil, the clay that have ever been experienced. We call that it go beyond the maximum pass pressure. So the piece of C here, as you can see, is stand for the past maximum consolidation stress. So he also point out a very important concept in geotechnical engineering, which is soil or the clay you remember. So what does it remember? You remember the maximum stress level or the maximum loading that it has ever been experienced. Imagine like a piece of soil elements in the ground for many years, 1,000 or 10,000 or like a long history of geological time. And throughout the time, erosions happen. So you could have like 100 feet of soil above it got eroded, or like man-made activities. In the past, he has experienced a structure on top of it. Now the structure is gone, and the stress used to be above it got released it, but the soils in the ground, you remember, because the loading on top of it in the past, it can attribute to the structure of the clay, which is like a bunch of clay mineral that interact with the water. So again, like if you have a piece of soil elements in the ground, and this piece of soil elements, you remember the maximum past pressure, because this could be like a year 2022, but could be like 2,000 years ago. Maybe this is like a year of like 22. There used to be a bunch of like a soil or another like stratum soil on top of it, but because of erosions, and now this is gone. But like what the soil remember is the stress that used to be acting on top of it. And this, like, what you remember or the stress that used to be on top of it, yes, can be recovered from engineering plot here, which is this point. So this piece of C represent the stress level, the maximum past pressure that in the past. And again, we can recover it in the lab if we take the soil elements, ship it back to the lab, put in the odometers to run a consolidation test. Then we can recover this piece of information. And if you want to learn more about the consolidation lab, please go back to my CE 368 consolidation lab. And we will work on given the information in the lab, we will work on the lab procedure per ASTM standards to walk you through how to recover or how to generate this E-log peak curve right there. Essentially, it's like all the lab work that we do is try, a lot of effort is to try to recover this maximum past pressure, and also the C sub R and C sub C index, the slope of the lines right there, such that we can have those three parameters to do our settlements analysis, which will come to the equations later we talk about. But here again, very important concept. Understand why what does this piece of C mean, or how does graph work? Again, this graph tells you how the clay particles or the clay site will perform when it under stress or when under loading, because you can reflect in, or it depends on the maximum past pressure that it has experienced, and also the corresponding stress level, whether less than or higher than that. And then you can come with the or it can be like described by the slope parameters here, C sub R or C sub C. So this is the piece of C concept, and the current stress level, you can see like you have a P sub log right there. So P naught there means the initial effective stress, consolidation stress, which means right now in the site, what is the stress level? This is the P sub naught, which is now. And another concept here is the P naught plus delta P. So P naught plus delta P is kind of like the final stress. The final stress because of like your project. It could be like the same site. But so this is your elements in the past, used to be a piece of C, but now we know that there's like an initial stress and your project site, including a structure on top of the clay site, and this give you surcharge loading of delta P. So the final stress will be equals to the initial stress plus the surcharge, but with influence factors. So the influence factors is the one that to correct because of the depth effects. Because the loading right on the ground surface is exactly what the surcharge is, but with the increasing depth, the loading that given from above the ground will decrease with the increasing depth, and that is taken care by the I values right here. So pretty much this I values, or like to be more clear, to be consistent with the FE manual. So the final stress is equals to the P naught plus the surcharge, and the surcharge we need to take account of the influence factors. But this is the final stress. So in settlement analysis, you realize your initial stress and final stress, how it relative to the maximum pass pressure is very important, such that like it lies into the three equations right here. These three equations here pretty much give us three different scenarios. So I call this case 1, case 2, and case 3. And essentially, these equations pretty much is it try to solve for the it's a point slope problem. Try to solve for the change of wall ratios, and the change of wall ratios is related to the deformations, which essentially also you can see from this formula right here. So pretty much delta E is related to the delta H, which is the deformations with these equations. And or like, we organize it, the delta H is again related to the delta E. And the delta E here is pretty much just the y-axis, the change of the y-axis, and H naught is the original height of your original thickness of your clay deposit. So this is like kind of like the H naught, and the E naught is the initial void ratios, which is this point here. So with all this multiplying by this constant here, we can relate the change of void ratios with the deformations. So this is what we can measure in the lab, and we can correlate with what we anticipate how much deformations in the field. So that's like a three equations right here. Pretty much like you can tell this part, the delta H right there, is related to our delta E. So this is our delta E. And delta E have three versions: case 1, case 2, or case 3, based on, again, how our final stress and initial stress. So this is my initial stress, and this is my final stress, how we compare with the maximum pass pressure. So case 1 is the scenario that, so this is case 1. So again, this is the consolidation curve as if in your FE manual. So every time when you have a settlement problems, it's always great to start to draw a picture of the consolidation curve first. And you know, this is the point of your P sub C, and this is your C sub R, and this is your C sub C, just like your in your FE manual, the consolidation curve. And case one is the case that both your initial stress and also your final stress of the pressure is both less than the P sub C. So this is the P sub naught, and this is the P sub F. So that is the case one. So when we do our settlements analysis, what we want to deal with at the end of the day is the delta Y that talking about this 2 points. So this is my delta E right there, which is if this has become a point slope problem, like you know the slope, like we run algebra, the slope is equals to the delta Y divided by the delta X, right? And now the case that we have, the slope is C sub R, and delta Y is what we want to look for. And then like the stress there is the delta X. So this is what we want to solve for the delta E. And this case, since we have a semi-log scale, then it becomes the log of stress 2 divided by stress 1. So which is like this formula here. So essentially, this is the delta E. The delta E equals to the C sub R times what we want to have here, the finals divided by the initials. And this is case number 1. And case number 2, so this is case number 1. And case number 2 is, again, the same picture. The stress, the maximum pass pressure. And this time, for the case that both initial stress and the final stress are both greater than the maximum pass pressure. So essentially, we are solving for this delta E right here. So this is my delta E again, with the slope of C sub C only. So this is case number 2. And for case number 3, oops. For case number 3, now is the time that we have 2 portions of slope, because my initial stress and final stress is sandwiching the maximum pass pressure. So that's why now I have 2 parts of slope. So this is my first part of slope. So this is the delta E1, and this is my second part of slope, delta E2. So essentially, this is my delta E1, and this is my second part of delta E2. Again, it's just like a point slope problems that you want to solve for the delta E, because delta E times the some factors can give us the deformations. And the delta E now for our third scenarios, you will have 2 parts, because we experience the 2 slope portions, the C sub R right here, and the C sub C right there. The compression index and the maximum compression, the V compression index, and also the compression index. So this is what essentially those formula, yes, and I will have another tutorial lectures to walk you through some example problems applying those formulas. So this is essentially like, you know, the formulas we talk about, and this is in a little bit more details now to tell you how to calculate C sub C if you're given a consolidation curve. And realize that so this formula gives you the basic, but realize that like when you are given a consolidation curve, because we are dealing with a negative slope, as you can see the consolidation curve here, you have a negative slope. So when you pick a point, you better like consider the negative slope. So essentially this means like something like this. Consider the fact that you are picking 2 points. So this is a C sub C. So you are picking 2 points right here. So this is your sigma of the P1 and E1. And this is another point here, P2 and E2. So as long as you pick those two, any 2 points along on the curve, you will use this formula to calculate either the C sub C or C sub R. And again, like, this FE manual just give you the basic of the basic, but in reality, when you do your calculations, you need to consider the fact that this is a negative slope. So we will multiply by the -1 there. And we will do some more examples in my next tutorial videos. So please subscribe to my channels, and I will upload more. I work on more example problems on my YouTube channels. So another formula here, pretty much this is give you a rule of thumb, kind of like a quick correlations of the C sub C related to liquid limit. So this is done by empirical correlations, which essentially researcher, they compile a lot of data from liquid limits and also the C sub C and the values, then they come up with a real wealth of correlations, pretty much like a kind of weak correlations to represent all the soils. But this is a quick one you can use to estimate C sub C when you given by liquid limit. So for the FE exams, when you see the keywords of liquid limits and C sub C, then you can record this formula, compression index and liquid limits. You can record this formula. Same as another formula here, if you're aware of rough estimations on the relationship of between C sub R and C sub C. As you can see on the slope right there, and physically it makes sense too. When the pressure go beyond the maximum pass pressure, which means go beyond the stress level that the soil has ever been experienced, then it start to collapse, or it start to accelerate the deformations of the soil particles, which involve the mineralogy and also the water reactions with the clay particles and clay minerals. You will accelerate the deformations when the stress level is go beyond the maximum pass pressure. So you see, that's why the C sub C slope is always greater than the C sub R. And by how much? And this correlations over there telling us in general is about 6 times. So the slope of C sub C is in general 6 times greater than C sub R. But again, that is a very wealth empirical correlations. It highly depends on the soil type. As you can imagine, if you have very sensitive organic soils, the slope difference could be greater. Versus you have a highly overly consolidated clay, then the difference between C sub C and C sub R could be much smaller. So, but in general, this is 6 times according to the FE manuals. And again, when in FE exams, when you see the keywords of C sub C and C sub R, given C sub C asks you to estimate the C sub R or the other way around, then you can record this formula. So after that, we also have the ultimate consolidation settlements in the soil layers. So pretty much just telling you the settlements is equals to the volumetric change of strength. So these are epsilon V here is the volumetric strength. And since we generally assume 1D consolidations, which means all the deformations happens at 1 dimensions, provided that we do reflect an infinitely long soil layers. So the deformations horizontally will be negligible, because like you have compared with a very long lateral soil layers versus you have a finite vertical depth constraint right there. So such that we assume all our volumetric strength only take place vertically. So it works in a way that the settlements is equal to the volumetric strain times the H of S, which is the thickness of the soil layer. And with that, we can so here the thickness is the soil layers, which originally I call H0. So FE manuals, this is the H of S. This is H of S. Okay, so the next formula pretty much here is repeating how to calculate the volumetric strain. And this is where I like, what we have been doing, previously from the formula. So the delta E total is the total change in void ratios. And delta E pretty much we can find by this set of formulas. Depends case 1, case 2, and case 3. It depends on how your initial and final stress compare with the maximum pass pressure. So if we can find delta E and we know the initial E log, then we can estimate the volumetric strain. So that pretty much concludes the first part, the compressibility of soil settlements. The next is the time rate of settlements, and you come with this formula right here. The approximate settlements at a given time. So previously, the settlement that we calculate is the total settlement. So pretty much like saying we wait long enough, infinity of time. Eventually, is just the total settlements of primary consolidations that we calculated. But now, what happens? There's a time aspect. So if you take like 100 years to finish all the primary consolidation settlements, what does the settlement at time equal? 50 years, 60 years, 70 years. That could be your the lifespan of your structure that you're going to design for. So this formula become handy. This ST, the settlements that you want to calculate at a particular time, the ultimate settlement is the one that you calculate previously, and the difference between the two is with a factor. The factor is the UAV, U sub AV there, which is the average degree of consolidations at a given time, the time of T sub C. So elapsed time since applications of a consolidation load. So realize that, this there's a keywords over here since the applications of the consolidation loading. So the consolidations can be restored once you change the load, either you increase or decrease, then the clock will start again. And again, for more details, the Tosaki, the spring demonstrations, the spring model give a very good demonstrations on this concept. And for more details, please visit my CE 366 lecture number 9. So what is this UAV? So this UAV now become handy because if we know the UAV, then it helps us to find out the amount of settlements, and that is related to the average degree of consolidations. And the next table here gives you a different percentage of consolidations. You come with a time factors, the T sub V, and the famous Tosaki equations, which is here. So the T sub V, the time factors, because once you know the other nice thing about it is not just the amount of settlements at a given time, but also you want to find out how long it takes for the settlements to be occurred. So for example, if you know you want to know how long it takes for the 10% of settlements, because you realize the 10% of settlements it means the USAV, the percentage of consolidations, equal to 10% as well. So and the Tosaki theory gives you a corresponding time factor, which is here. And with this equation, this famous Tosaki equations here, if you know the T sub V and you know the HDLs, so HDL is a drinkage path, distance. With a constant of C sub V is the coefficients of consolidations, which can be measured in the lab. So again, like if you visit my consolidation lab, we talk more details about the log time and scale time method to per STM standard to how to measure this C sub V parameters in the lab. And again, HDLs is the water drinkage path, which is further explained in this 3 graph here. We need to consider the drinkage conditions. For the case that we have two-way drinkage, or some reference book or textbook call this to be the double drinkage, the double or the two-way drinkage, which means when you have your clay samples of clay layers sandwiched by two much more permeable or drinkable or drinkage layers like sand or gravels, sandwiching it, then which means the water can either go up or go down. And for the case that the longest distance will be happening at the middle of the clay layer, right? Because the water, the excess pore pressure, the excess pore water trapped in the middle in the clay layer can either go up or go down. So you have two different ways of drinkage. So that's why you can call it two-way drinkage right there. And at that times, your drinkage distance will be equals to half of the thickness of the soil layers. So this will be the HDL distance right there for double drinkage case. And for the case that you only have one-way drinkage, so this times, for example, here, you have a sand layers or more drinkageable layers or permeable layers on top of your clay. But underneath that could be just another clay. So this is for the clay layer. Or even backwalk, intact backwalk. So there's no chance for the drinkage. In that case, the clay that the water that excess pore pressure or excess pore water get trapped at the bottoms of the layers, it can only go up. So the longest drinkage distance will be equals to the whole layers. So this time becomes previously we call it as the H sub S, right, the thickness of the soil layers. Instead, like previously, when you have double drinkage, it's equals to half of the thickness of the layers. Now, for single drinkage is the whole layers that to be your drinkage path. And very similar, the same case, you have the impermeable layers only with a drinkage layer underneath it, so all the water need to go through the whole thickness for a case that pore water trapped in the topmost for this case. And the drinkage distance again would be equals to H sub S. So this walk you through some concept of the time rate of the settlements or time rate of clay primary consolidations. For my next YouTube videos, I will talk more. I'll work on some examples on these two topics, and for more details, please go back to my C366 lecture and stay tuned. Subscribe to my YouTube channels for more FE example solving.